Okay, welcome to today's lecture on scattering theory. Today I would like to begin with chapter 4. Chapter 4, which is Kato-Bürman theory. Yeah, and in some words, what is our goal here? We will first of all discuss the so-called trace class. So our goal is to understand what are trace class operators. And this trace class will be denoted by B1 of H. And then we will assume that the difference B minus A for two self-adjoint operators B and A with the same domain, we will assume that this difference is a trace class operator, and then we will conclude that in this case the wave operators for the pair AB they exist and are complete. This is the so-called Kato-Rosenblum theorem. First of all, and another theorem which is important for applications when you think of Schrödinger operators, for example, we will assume that the difference of the resolvents, so B plus I to the power of minus 1 minus A plus I to the power of minus 1, that this operator is trace class. And then we can show that, again, omega plus minus of AB exist and are complete. And this is the so-called Kuroda-Bürman theorem. Yeah, and both theorems will follow from Pearson's theorem. And we will give a detailed proof of this important theorem here in this lecture. So here, of course, as I already said, A and B are self-adjoint operators, of course, in the Hilbert space H, and this result here is of particular importance for Schrödinger operators. So this has applications for Schrödinger operators. In particular in R3. Yeah, so this is our plan for the next lectures. And now I would like to start with the definition of the trace class. So let's start directly with the following definition. Definition 4.1. Yeah, it's a little bit more general, but this will be very useful, as you will see in the following. So for P between 1 and infinity, and infinity is excluded, as you will see, and we allow that P is equal to 1. So for these values of P, let Bp of H be defined as follows. Let this be the set of all compact operators that I denote by B infinity of H, such that the sum of the singular values uj to the power of p for j running between 1 and infinity is finite. And we call this class the so-called Schatten von Neumann class, the Priv Schatten von Neumann class. So let this be the Priv Schatten von Neumann class. Yeah, and we have to add here the class B infinity of H is the compact, denotes the compact operators. So this denotes the class of compact operators on H. And the sequence mu j for j element n is the sequence of singular values of A. Is the sequence of singular values of A. Which is a compact operator. Yeah, so recall from basic theory, if you have a compact operator, let's say A, then these singular values are the eigenvalues of A star A. Yeah. So we have that mu j is an eigenvalue of A star A. And these eigenvalues are repeated according to their multiplicities, of course. And furthermore, we have that because of the fact that we have that A star A applied to some u times u. If you consider this quadratic form, then of course you can throw the A star to the other side. So this gives the norm of AU to the power of 2, and this is non-zero. And this shows that the mu j, if you apply this here to suitable eigenfunctions, then you see that uj has to be non-negative. Yeah? Okay. Okay. Furthermore, I would like to add here, we call the class B1 of H the trace class. And we call B2 of H the so-called Hilbert-Schmidt class. These two cases are important to keep in mind. Furthermore, we have the following remark. It's remark 4.2. And there is an analogy between the spaces BP, so between the spaces BP of H and LP, small LP, for one smaller than p smaller than or equal to infinity, but it's important to note, however, L infinity, which corresponds to the bounded sequences, corresponds of course to the bounded operators, so corresponds to L of H, the bounded linear operators, and not to the space of compact operators B infinity. Of compact operators B infinity of H, so that this notation is in some sense not ideal, if you understand what I mean. In this regard, the notation B0, of H for the class of compact operators would be more appropriate. For the class of compact operators would be more appropriate. So this is a remark concerning my notation. Okay, then let's continue here with the first theorem. So this is theorem 4.3. We claim that for p bigger than or equal to 1 and smaller than infinity, the class Bp of H is a two-sided star ideal in L of H Yeah, meaning precisely that. First of all, if I take an element A in this Bp of H and I take a complex number lambda, then we have that also a star, this refers to the star here, is again in Bp of H, and also lambda A is again in Bp of H. Secondly, if I take two elements, A and B, from Bp of H, then the sum is again in Bp of H. And finally, if I take A in Bp of H and I take a bounded operator, a bounded linear operator B, then we have that if I consider AB and BA, these are both elements of Bp of H. This refers to the property that we have a two-sided ideal in L of H. Yeah, I think the proof of this, okay, it's, I have given a reference for the proof, so the proof of the statement can, for example, be found in Reed-Simon, volume 1. There you find it as theorem 6.19 for the case p equal to 1. So I will not go into details here because it's very elementary. Instead of that, let's go on with the following theorem. Yeah, first of all, let's remark the following thing. This is important. So the space of compact operators so in my notation it's this B infinity of H. This, of course, as you know, is closed. This is closed with respect to the usual operator norm. And for the other classes, this is only true for certain stronger norms. So for the ideals BP of H, this is true with respect to certain stronger norms. So this holds true with, or let's say for certain stronger norms. And this is what I would like to consider in theorem 4.4. So theorem 4.4, let again P be between 1 and infinity, and I exclude the compact case here, and define for an operator A in BP of H the following norm. I define the norm of A in BP of H simply by taking this finite sum J running from 1 to infinity of the singular values to the power of P, and then I take it to the power of 1 over P, and then I claim then this BP, this norm here is indeed a norm. Then this is a norm on BP of H, and BP of H is closed with respect to this norm. And again, I only give a reference for the proof as, it's in some sense standard. So if you're interested in a proof of the statement, then you can look in Weidmann's book. Yeah, Joachim Weidmann, the first volume of this, and there you find it in theorem 3.22b. Okay. Interesting is for us and for our purposes is the following theorem. So theorem 4.5, which refers to some remarkable properties of the classes B1 and B2. Yeah, in particular, it has three parts. First of all, let A be a bounded linear operator on the Hilbert space H, and let J, for J in N, be an orthonormal basis for H. Then I claim then the sum, then the following sum for J Ej running through n of norm A Ej to the power of 2. Of course, yeah, this object cannot be negative. It can be 0, but it cannot be negative, so it has values in the interval from 0 to infinity. And of course, for general A, we cannot exclude that this value is infinity here. So I have to consider this case here. But that's not the interesting thing. What I would like to claim is then this sum is independent of the choice of the basis. Is independent of the choice of the orthonormal basis. So let's continue here. Is independent of the choice of the Ej. Of the choice of the basis Ej for the Hilbert space. Property number 2, for A in the Hilbert-Schmidt class, so for A in B2 of H, I claim that this sum here is precisely the norm, the B2 norm of A. So we claim for A in B2 of H, we have that the norm of A, this B2 of H norm to the power of 2, is nothing but the sum that we had in step 1. For any orthonormal basis J of H Yeah, so here you see that step 1 is indeed important to obtain that this object is independent of the choice of the particular basis. Yeah. And finally, number 3, we also have that A is in the class B2 of H if and only if the sum over J of the norm of A Ej to the power of 2 is finite, and this holds for some orthonormal basis. For some orthonormal basis Ej of the Hilbert space. And the proof of this theorem, this is an exercise for you, and it's on the sheet that I have prepared for today. So this is exercise 14, which we will discuss next week. Maybe this is a good time to provide you with these exercise sheets. Here they are. Okay. And then we can continue with theorem 4.6. So, theorem 4.6. Here I consider an open subset of Rd, so let omega in Rd be open. And I consider a bounded linear operator A in L of H, where the Hilbert space H simply is the L2 space of omega. Then we claim then A is a Hilbert-Schmidt operator is a Hilbert-Schmidt operator if and only if there is an integral kernel K capital K, which is L2 on omega times omega, such that we have the representation that A applied to a function f at x is given by the integral over omega k of x and y, f of y dy, and this holds almost everywhere. Yeah. Again, I will only give a reference concerning the proof where you can find it. For example, proof can be found in Weidmann's book, volume 1. There it is, theorem 6.11, and you can also look it up in Reed-Simon, volume 1. There it is, theorem 6.23. Yeah, so we will not go into further details here. Okay. And finally, we also have theorem 4.7. Theorem 4.7, it says that A is a trace class operator if and only if there are operators BC in the Hilbert-Schmidt class in B2 of H with the property that A has the decomposition BC. And this is again an exercise, so the proof of this is on the exercise sheet for today, and it's exercise 50. So you can prepare this until next week, and then we will discuss the solution. Okay. Given a compact operator A, with the singular values mu j. Yeah, of course, as a short reminder, you know that for compact operators you have this representation using singular values in the following sense. You have here these singular values mu j, and then you have two orthonormal systems, let's say vj and uj, such that a representation of this form is possible. Yeah, this is always possible for a compact operator. And we also already said that these mu j are the eigenvalues of A star A. So given a compact operator A with this decomposition and the expansion that A star A is given by, of course, this is a symmetric operator here. So we have the representation j running from 1 to infinity, mu j to the power of 2 then. And here we have an orthonormal system xj. Yeah, precisely the mu j to the power of 2 are the eigenvalues of this object. This is important, yeah? So you have to take the power of 2 of these values to obtain eigenvalues. This is what I meant. For some orthonormal system xj, xj, j element n, we define the absolute value of A by following way. The absolute value of A is defined by the sum j running from 1 to infinity, and here we simply take the mu j and here the scalar product with the xj times xj, and you see that this is nothing but the square root of A star A. Yeah, this is important to know this notation. Maybe we look back onto the first blackboard. Maybe this was not clear enough from my side. Here we have to correct that this is the case. And then we assume here, so assume that for simplicity, assume that the mu j are non-negative, so that this representation here makes sense. Yeah, you know what I mean? So that this here makes sense, I assume that the mu j is non-negative, which of course is no restriction. But please correct this. This has to be taken to the power of 2 here, and then the same argument as I presented goes through, and then we assume that the mu j are non-negative to have a suitable definition here. Okay. Yeah. Okay. Then we come to theorem 4.8. Theorem 4.8. And first of all, we claim that A is in the trace class if and only if for any orthonormal basis for any orthonormal basis AG, G in N, for H, for the Hilbert space H, we have that the sum J running from 1 to infinity of the operator absolute value of A applied to Ej times Ej is finite. First of all, and the second statement, number 2, statement number 2, for A in B1 of H and an orthonormal basis Ej and an orthonormal basis Ej of H, we claim that the so-called trace And this is why we have this name trace class. We claim that the trace of A, which is defined by the sum J running through the naturals, scalar product AJ, A applied to EJ is well defined. In the sense that the sum converges absolutely. The sum converges absolutely. And is independent of the particular choice of the basis. And is independent of the choice of the orthonormal basis. Of the orthonormal basis EJ of H. And this will be on the exercise sheet for the next week, which I will give you next week. So this is exercise 16. So the proof is exercise 16, which will be on the next sheet. Okay, one final remark to all this introductory stuff. Remark 4.9. Yeah, so remark 4.9. We denote the eigenvalues of a compact operator A by, let's say, capital lambda J. Of course, these are complex values, and J is in some index set M, and we have three possibilities. So we can have that, of course, the set M is empty. Yeah, this is the case when we do not have eigenvalues. It is possible that the number of eigenvalues is countable, so that M is equal to the naturals, or it is possible that M is a finite subset of N, so M consists of the natural numbers 1 to k. And it's important to know that in the general case, so in the non-symmetric case, a compact operator may have no eigenvalues or only a very small number of eigenvalues. Yeah. So note that a non-symmetric compact operator A may obtain no or only a very small number of eigenvalues. So may have no or only a very small number of eigenvalues. Okay, and then we define the so-called algebraic multiplicity of such an eigenvalue lambda j as follows. we denote the algebraic multiplicity of lambda j by mj, which I define as follows. I take the supremum for k in n of the dimension of the null space, so the kernel of the operator A minus lambda j times the identity to the power of k. And concerning this object, we have to explain some things. So let me clear the blackboard, and then we will understand why this makes sense. So concerning the algebraic multiplicity of such an eigenvalue, we can remark the following. This supremum that I had defined on the other blackboard is finite for any j as far as the lambda j is non-zero. Is non-zero, more precisely, we have the following. For any lambda j non-zero, there is a kj in n. There is a natural number kj with the property that the null space of A minus lambda j I to the power of kj plus 1 is equal to the null space of A minus lambda j identity to the power of kj, meaning that for k bigger than this kj, the null spaces of A minus lambda j identity to the power of k are equal. Yeah, and then there's a famous theorem which I only cite. You can find it in Reed-Simon's book in volume 4. It says, so by the so-called Litsky theorem, one then has that for A in the trace class, one has that the trace of A is then given by the sum for J running through the index set M. That could be, of course, empty, but then the other cases where that it is empty, so it's a finite subset of N, or that it is N. And here we have the multiplicity Mj times the lambda j. And you can look it up in Reed-Simon volume 4, where it is on page 328. But we will not apply this Litsky theorem henceforth. It's only to show what is possible with this formalism that we have now. What we will actually need is the following definition. It is definition 4.10 concerning cyclic vectors. So let A be, of course, a general unbounded operator in H. Let this be self-adjoint. A vector phi in the domain of A is called a cyclic vector for A is called a cyclic vector for A if phi is also in the domain of A to the power of k for all k in n. So for k in n. And we have that the span of phi, A phi, A to the power of 2 phi, and so on, and all these objects are defined since phi is in the domain of AK. And we have that this span is dense in the Hilbert space. Yeah, to have such a cyclic vector, of course, is a very strong claim, but nevertheless, it is possible to consider a decomposition of the Hilbert space so that on each component of the Hilbert space one has such a cyclic vector. This is what I would like to present here in remark 4.11. So remark 4.11, the existence of a cyclic vector is a strong claim. This is a strong claim. Nevertheless, for A self-adjoint and H separable, for A self-adjoint and a separable Hilbert space, one always has a direct sum decomposition of the following form. One always has a direct sum decomposition of the following type, that H is a direct sum of n spaces Hn, where this capital N is either a natural number, and we also allow the case that n is infinity. So one always has such a decomposition such that A leaves each Hn invariant, each Hn invariant, and for any n there is phi n which is cyclic for the restriction of A to the Hn. Okay, and finally, for today, I would like to present the multiplication operator version of the spectral theorem. This is what we will need in the following, so it makes sense to look in detail on this. So we here provide the multiplicator form. So the multiplicator, or let's say multiplication operator form of the spectral theorem. And this establishes a unitary equivalence to multiplication with a variable lambda in a suitable L2 space. So we establish the unitary equivalence of a given self-adjoint operator to multiplication with lambda, so with the variable lambda in a suitable L2 space. And this theorem reads as follows, theorem 4.12. So let A be a self-adjoint operator in the Hilbert space H. Be a self-adjoint operator with a spectral family E of lambda for lambda in R. And we assume here that A has a cyclic vector. Assume that A has a cyclic vector phi. Furthermore, let mu phi be the Borel measure let this be the Borel measure associated with the function, with the usual function, so with the function from R to C, given by the map lambda is sent to E of lambda phi phi. This means that concerning this measure, mu phi, that mu phi acts on sets from -infinity to t, let's say, in the sense that this is simply the scalar product E of t phi phi for t in R. And then we claim the following. Then we claim, then there is a unitary operator, then there is a unitary operator U from the Hilbert space to L2 of R with respect to this measure mu phi, with a property that AX is nothing but u to the power of -1 applied to the multiplication operator for the variable lambda applied to ux for all x in the domain of A. So this theorem establishes unitary equivalence of the operator to multiplication in this L2 space. Yeah? And this is what I would like to prove finally for today. So let's have a look at the proof of this important theorem. Proof. We define the operator U by setting U acts on f of A phi in the sense that this simply gives the function phi for any f in CC of R. Yeah, so recall, U is an operator that acts on elements of the Hilbert space, so on vectors phi, and it transforms to an object in L2. Yeah, such a function f in L2 later, but here we work basically with a dense subset C of R. So we first of all define this object on a dense subset, and then we extend everything. And this is the way in which I would like to do it. And then we apply the spectral theorem and apply the spectral theorem in the version that we had at the beginning of my lecture, so in the functional calculus version. To obtain the following. Now this object f of A, if f is a CC function on R, was well defined using this functional calculus, and we know that the norm of this object applied to some Hilbert space element phi to the power of 2. This is okay, but the definition of the norm, first of all, this. So this is clear, but this is then also the absolute value to the power of 2 of A, phi, and now we can use the spectral theorem in the way, or in the version that we already had. And we know that this is the function, so this f applied to the lambda, and here we also have the absolute value to the power of 2, d e of lambda phi. This is the spectral theorem in the version that we already know. Yeah, but then it's clear that this here is nothing but the integral over R of absolute value of f of lambda to the power of 2, and here we have integration with respect to this measure mu phi, so that this here is nothing but the norm of f to the power of 2 in L2 of R with respect to this measure mu phi. Now we observe the following. Let f and g be two functions in CC of R, and assume that f of A equals g of A. Yeah, by the arguments above. So here on the other blackboard, this refers to my script, and we obtain that f of x has to equal g of x almost everywhere. Yeah, this follows from what we had observed here. Assume that f of a equals g of a, then we obtain that f has to equal g almost everywhere. Precisely, there is a Borel null set. There is a Borel null set, let's say n, a subset of R, with the property that with respect to this measure mu n, the measure of this n is 0, so that we have that f of x is equal to g of x for all x that are not in n. Yeah, and then this defines an equivalence relation. This defines an equivalence relation on CC of R. So that U as a map now on the set of all f of a phi for f in CC of R to the set of equivalence classes is well defined. And also isometric. Yeah, so let's recall what we are doing. We take an element f of the CC space, which is a dense subspace of L2. We will need this later. And then we take a Hilbert space element phi and consider this element of the Hilbert space. And if you go back to the definition of U, you see that U operates on the Hilbert space and maps to L2 in this form here. Yeah? So we have here our Hilbert space object and it's mapped to this function f. And our calculation here shows that we have a well-defined object when we are dealing with these equivalence classes that I had explained in detail there. And furthermore, we have the property that this map is isometric. Yeah. Okay. Now, as our vector phi is cyclic, we have that the set f of a phi for f in CC of R is dense. We find that this is dense in H, and then by the so-called BLT theorem, or BLT, bounded linear transformation. This is a standard theorem in Reed-Simon volume 1. And then by the BLT theorem, we can extend we can extend U to an isometric map U to an isometric map from H to all of L2. Yeah, furthermore, as CC of R is dense in L2 of R. This is also again standard, and we find that the range R of U is dense in L2 with respect to this measure mu phi. Yeah, and furthermore, as U is isometric, we also find that its range is closed. Yeah, this is elementary. Its range is closed. So that, in fact, yeah, we have a dense subset in L2, and we have the property that the range is closed, so that finally we must have that the range of U is equal to L2 of R d mu phi. Yeah, so this shows that our map is surjective. It's also isometric, so we finally get that U is unitary. So we have a unitary map here. Okay. Finally, for F in CC of R, the fact that recall the definition, U to the power of -1 applied to F is equal to F of A phi. This is basically a different representation of the definition of the U. Recall that in the definition of U we had U on this side here. Yeah? So I know that U is a unitary map, so I have U to the power of -1, and then I can rewrite this equation in this form. And the fact that this holds true implies that U to the power of -1f applied to lambda. What is this? This is nothing but U a f of A phi of lambda. Yeah, U to the power of -1f is f of A phi, so we have this here. And we now define a map F twiddle in CC of R by setting F twiddle of lambda should be lambda f of lambda for lambda in R. Lambda in R, so that we have that F twiddle of A is equal to A f of A. Yeah. Then we get that U to the power of -1f of lambda. What is this? look at this line then, you see that it's u f twiddle of A phi applied to lambda, at the argument lambda. Okay, and what do we find here? Okay, let's go back here. We have here this f twiddle. Okay, and now we simply apply the definition of u, which says that this is nothing but f twiddle of lambda. Yeah, so this is simply the definition of u, and now we have here f twiddle instead of f. So this gives f twiddle of lambda, and by the definition, this is lambda f of lambda. And this is what we want to have. Finally, as Cc of R is a dense subspace, it's dense, this extends to all of L2. And this completes then the theorem, the proof of the theorem. Okay. Finally, one remark. Remark 4.13. If there is no cyclic vector for A, if there's no cyclic vector for A, there are Borel measures mu n. There are Borel measures mu n, and there is a unitary operator in the following form. U is defined on A and maps to the direct sum I running from n, let's take small n here to capital N, and here we have two spaces, R d mu n, and here again n is an n, or n can be infinity, that provides a spectral representation of the operator A. Yeah, so that provides a spectral representation of A in the sense that u to the power of -1 phi, and then the nth component of this object, yeah, because the map u arrives at this direct sum space, this is equal to lambda phi n of phi, and here we have that any phi in this direct sum space of the L2 are, with respect to the measure d mu n, can be identified with such a tuple phi 1 of lambda, phi 2 of lambda, and so on. And again, I only give you a reference where you can find this. So you can look this up in read Simon's book, Volume 1. There you find it in Theorem 7.3. Yeah, and finally, if A has purely discrete spectrum, then each eigenvector of A is associated with one copy of these L2 spaces, and the associated measure, and UN, is then a point measure that concentrates its mass on the corresponding eigenvalue. Concentrating its mass on the corresponding eigenvalue. Okay, I would like to stop here for today. In the next lecture we will continue here, and then we will work towards Pearson's theorem, which is the basis for the applications that I presented in the introductory part of the lecture for today. Okay, I thank you for today, and then we'll see again next week, and in a few minutes I will continue with the exercises. So, thank you.